I might start by telling you how I got the Order of Australia. I was interviewing students for a scholarship yesterday, and it seemed to be the major question they wanted answered. When I started doing this, I've been involved in... I'm actually a professor of digital forensics. They forced us to have this cybersecurity title, but digital forensics is what I've done. And I started in the old days before e-crime labs had really been developed. And then we went through 9/11 and issues in terrorism, where we just had heaps and heaps of data. With my students, we did things like data visualization and all the rest of it. And I basically gave the federal government a lot of my time. They helped me get grants, never got any. I never would have wanted money. So they gave me, the AFP sort of gave me, as it were, gave me the Order of Australia. And if you look at the citation, it says things like cyber terrorism. But I've never ever seen a terrorist. I'm not a spy. All I've ever done is, the whole theme of my research has been to understand about devices and how they are, to what extent they are insecure, then to wonder what the bad guy, whether the bad guy is the enemy of the army or a terrorist or a criminal, what they might do with it. And I'm always trying to be one step ahead of the criminal because I work with law enforcement for so much. Policemen are not trained in IT, let alone cybersecurity. So it's to be able to go to the police and say, look, here's the device, here's the weakness, this is what the bad guy is going to do. So that's kind of the theme of my work. So I'm presenting to you a talk that I've actually presented to February. I've presented this to engineers, particularly Engineers Australia. So I've prepared this for technical people who have a mathematical kind of background, and that's what I could think of statisticians, who may be interested in cybersecurity but may not really understand what it is that people like me do, because we use this term so blandly. And if we were to think about undergraduate mathematics or undergraduate statistics or engineering, we would actually, between us, know what exactly was in a curriculum. But with this thing called cybersecurity, we often have no idea. Because even though we keep developing standards and definitions, we can put social science in there, we can put law in there, we can assume high school mathematics, or we can assume what we normally get, that if you put a sigma on the board, everybody's going to run away. So we teach I've taught for many years cryptography for the non-mathematical. We can teach most subjects to the non-mathematical, looking at my colleagues here. So we live in this sort of bubble in between science and its application, or mathematics and its application. So the reason I looked at machine learning, I've extracted something from a paper of which I've done based on work that a PhD student of mine, who's still at UNSW, did, to try to explain really what do we use machine learning for? Why are we using machine learning? How do we develop things like intrusion detection? For me, intrusion detection systems, network forensic systems, using artificial intelligence techniques. So machine learning is a data analytics techniques that teaches computers to learn from experience. I think, and particularly in this university, we have people who are much better than I am with machine learning. I'm the person who needs somebody else who's more mathematical to tell me which algorithm to use, okay? I admit that up front. We have people, but then we have other sets of people who can, as it were, manipulate the algorithms, but they don't really want to apply them in my context of cybersecurity. So one of the things I was really grateful about when I came here was I found by collecting everybody together who'd ever worked in cybersecurity, but people who work here would know Naveen Chilamkirti. Naveen's great with cybersecurity and machine learning. So what I'm looking for are the people who've come out of that really rich mathematical background, and they've often come from India or South Asia. I'm British, obviously, from the accent, so we're okay at maths if we were engineers like me. But it's trying to bring together the mathematical understanding in a world where the people who are learning cybersecurity are just generally those IT people who haven't gone deeply into the mathematical. So what we're doing is we're using computational methods to learn information directly from data without relying on predetermined equations as models. Like this is what we've done over the years. We've coded. And we train these models with large amounts of data, and they can be supervised or unsupervised learning algorithms. So if it's basically supervised learning, we have a known set of input data and known responses to the data. We train a model to generate reasonable predictions to be able to respond to new data. And you use this where there's known data for the output you're trying to predict. And we have different kinds of classification techniques for discrete responses and regression techniques for continuous responses. But we also have unsupervised learning algorithms which finds hidden patterns or intrinsic structures in the data, draws inferences. And clustering is the most common unsupervised learning technique we're using. So we get data. For us, maybe that's network streams or other kinds of data anyway, to find hidden patterns in the data. So what we're dealing with is in a world that we know, where it's known data. The problem is, in cybersecurity, there's been a total paradigm change. And this has happened really quickly. So I probably started in what was called cybersecurity by about 2001. And I worked with the federal police in the early days of trying to get data off of mobile phones. In those very early days, there was not much in the way of sort of intelligence in a mobile phone. And the biggest problem we had was making sure we had the right sort of cable to extract the data. Because if you remember the old days, every vendor had a different cable. And I was at UniSA in Adelaide at that time. I had heaps of honours students. So they had this grand idea I was going to be able to develop standard operating procedures for every single mobile phone. And I was going to document them so that they'd just take them to their police station and they'd know exactly how to extract the data. And in those days, what we were really looking for was evidence. And there was really only a small amount of evidence anyway. And the people who were working in that area were generally people who come out of the fraud squad, or else they'd been dealing with sex crime, because they were the only people who dealt with anything like a computer and later on mobile phone. But in a very short period of time, we moved from worrying about the cable, and later on we had to work with the hardware, the little tags on the back, the J tags, because we could dump all the data and collect the data. And then we moved to things like, I can remember certain dates and certain cases, like there was a bombing in London with a bus and on the underground in 2007, and a crime scene where there was of the order of 60 devices. And so I can remember asking the research question. I had some money from Prime Minister and Cabinet, which was for counter-terrorism, because we were assuming that those kinds of things would happen. So it was, what will we do when we've got a crime scene with 60 devices and we don't know who they belong to? Is there some way that we can actually match up, which of the owners of which devices did they know each other? So that's when we started doing that sort of social networking stuff, when the data grew, and that's when we went into visualization. So I came out of mechanical engineering. My PhD is in science education. A lot of what I know is self-taught. But I got to the stage where I was going from this area to this area to this, to be the best applied researcher that I could be. And I actually so I took long service leave and had a break. And I had been saying, and that was 2012, and I had been saying to myself, I'm never ever going to deal with AI. I'm never going to deal with machine learning. I don't want to have to do this. I was saying, you're getting old, you don't want to have to go back and relearn all that maths. But I came back from Namibia, where I met Stanley over there, and I realised, oh my goodness, everything is AI and machine learning. I'm going to have to do this. So we've moved from, can I suck something off a single phone, to needing to deal with huge amounts of big data from sensors and devices. And for people in our field, we cannot refuse to engage with this big data. But if you're my generation, and my generation in cybersecurity or forensics, we're a whole collection of odd qualified people. You know, we might be physicists or mechanical engineers, and there's lawyers, and my mentor is has got a PhD in international law of the sea or something like that. But we're those weird people who are interested in everything and have learned to do a bit of maths on the way. And we're often dealing with the applied areas. So I decided that with the growth of almost the obsession with putting sensors on things, and dealing with the Internet of Things, that was going to be an area where I was going to have to specialise. So what I'm saying is then that digital forensics is an example of where we've had to use machine learning to build technical capacity because the applied problem has grown so quickly over what is a fairly short period of time. You might want to say 15 years or something like that. And for science, if you want to call it science, that is a short period. So I'm drawing on a paper that that my PhD student and I did. It was called Towards Developing Network Forensic Mechanism for Botnet Activity in the Internet of Things. So it means, imagine the Internet of Things, where you've got so many devices connected to the Internet, things that should never have been connected, in my humble opinion, like cow trackers. You know, they track cows to, I think they track cows to find out about the milk. I haven't quite worked out every detail of cow trackers, but I do know that they have been used as a for denial of service. So we get the processing power of all these tiny cow trackers, and somehow, being a very clever criminal hacker terrorist, we can actually use those for attacking somebody else, the processing power. And I think it was at the end of 2017, MIT, you know, the real MIT in America, one of its research things was looking at botnets in the Internet of Things. Supposing we could put botnets, bots, automatic bad bits of software in the Internet of Things, and I'm assuming that, you know, all the cows have got little bits of malware in their cow tracker. Or, as we saw with the attack on, is it Krebs? Krebs on security. That guy, he got attacked through all little tiny weeny cameras in computers, really cheap cameras. So anything that's a sort of a non-patchable device connected to the Internet can be used by clever hackers as a sort of source, a springboard to attack something else. So I usually get interested by obscure things. So me and MIT decided to look at this, and I had a PhD student who was just with a little bit of a push. I convinced him that this is what he wanted to do. Because it was like MIT. Okay, he's still at UNSW. I think he's finishing. I wasn't allowed to bring him with me. So network forensic techniques help us in tracking different types of cyber attacks. So we monitor a network or a system. So the forensic bit means I may be able to collect evidence or intelligence on the source of attack. So if I'm an intelligence agency or ASD or somebody, I might want to find out where the bad guy is situated. And if I'm the police, I might want to have robust evidence to go to court. So there's two. So if you're the police, robust evidence means you've got to collect much more detail, and you've got to be much more scrupulous in the sort of the science of collecting evidence. Intelligence is rather easier. So it's quite hard. The attackers are sophisticated. So we came up with a real-time collaborative network forensic scheme, and because working with machine learning actually requires lots and lots of data. This probably was 3 years of my 4 years at UNSW Canberra was trying to find a data set. So I set out with, because I've got a big network of industry partners, many times because my PhD students have gone there. So I started with all the known quantities like Cisco, and they all said, oh, Jill, go away. We've got whole factories of people like you. We've got data sets and you can't have them. And then I started talking to people in that community who were much more theoretical, much more well-known than me. And so they were saying, oh, Jill, we're looking for this data too. If you find some, can I have some? But then I said, well, I'm going to go and buy a traffic generator. I'm going to get synthetic data. And that community said, oh, Jill, it's not publishable. If you use synthetic data, you won't be able to publish it. So I thought, well, I've got a PhD student who can't do their work. You've got a PhD student who can't do their work because we don't have any data. I decided to take the risk that we won't be able to publish in IEEE and just create our own data set, basically. So I'll talk about creating the data set in a minute. So there's been a lot of work on botnets. So different security controls have been used. So we try to say define botnets. How do botnets work? What is it like? All kinds of tools and techniques. Intrusion detection. I can work out if there's a hacker in my system. Intrusion prevention, which means that an alarm goes off if the hacker's in the system. So mostly existing techniques use expert systems which generate specific rules in a blacklist, match the traffic against those rules. But we have used machine learning techniques to construct a network forensic technique based on network flow identifiers. So we know the source and destination IP addresses and the protocols. So I've got a little bit of a literature review which I will go through quite quickly. But essentially, and this is a very, very popular area of research, especially for PhDs, essentially all kinds of researchers looking at what they might do with machine learning techniques, because this has become more and more easy for us to do. So the techniques learn and validate given network data for classifying legitimate and anomalous observation, and they've been used for building network forensic techniques, but there's still two challenges to be addressed. One is that we can produce high false alarm rates, so we think something bad is happening and it's not really. And it's pretty hard to define the path of attacks, particularly in botnets, so there's a lot of literature on that. And many different algorithms have been used, including clustering, classification, pattern recognition, correlations, statistical techniques. So I talked about that before. So we're saying the research is popular, it's being done, and different techniques are being used to carry this out. There's a lot of work being done in different ways to detect and identify presence of botnets in networks, and we're using machine learning techniques on packets, which are often grouped into network flows, to just see the way the packets have flown through the network. So there are different ways that the malware gets delivered to the target, how it gets propagated. There's passive and active. So there's a lot of studies which have looked at machine learning to look at normal traffic in a network and botnet traffic. You can create intrusion detection systems for the Internet of Things to take into account wireless transmission, and loads of different algorithms, which I won't go into, have been used to try to enhance this research. Artificial immune systems as ways of securing the Internet of Things. Can I just mention the Internet of Things? The Internet of Things for me is really funny, because the Internet of Things is lots and lots of small devices which are impossible to do your Windows patching and update, because they don't have Windows and operating system. In fact, many people don't know that they have an Internet of Things device. They don't know the device is connected to the Internet. They don't know it's got an operating system. And even if they did know, they wouldn't know how to update it. I think you might think of cow trackers or something little like that. So about a year and a half ago to 2 years ago, well, a bit more was it? When was Turnbull Prime Minister? It was when Turnbull was Prime Minister. It seems a long time ago. Turnbull was an interesting guy because he once used to own his own ISP. He was an internet service provider. And so therefore he thought it was very technical. So he made the IoT a really important thing for us. And so some friends of mine at ASPI, which is the Australian Strategic Policy Institute, people who do policy in cybersecurity, were given the task of coming up with a scheme for the securing of the Internet of Things in Australia. So whatever we were going to do technically to secure them, he decided we were going to have the kangaroo tick of approval. So a really weakly secured IoT device has 1 kangaroo, and a very strongly secured IoT device has 3. That has always amused me. But the Americans have gone a little bit further, and especially in California. They came up with the idea that, well, if you want to use your IoT device, if you're the manufacturer or the importer, you've actually got to prove, it's almost like mathematically, that your IoT device is secure. And therefore, it had to have software that was updatable. It had to have passwords. You have to be able to change your passwords. And they've made the whole issue of the Internet of Things so hard, you probably can't ever put any IoT device on any government system in California. But it's obviously a big issue. So IoT is always very interesting to me because it's going to grow and grow. And for us, we're always importing them from Southeast Asia, where we have no way of imposing our criteria, our conditions, on the manufacturers who are manufacturing things so cheaply. It's not just a problem for us, it's for governments all over Southeast Asia as well. So all I've done in this work, this was the very first piece of work that this student did to look at machine learning in this sort of work with network forensic mechanism for botnet activity in the Internet of Things. So, and remember, I still claim to have my L plates on where the algorithms are concerned. So all we did is actually use 4 different easy classification techniques. A decision tree, association rule mining, artificial neural networks, and a Bayesian model for defining and investigating the origins of botnets. We were trying to see, well, whether these were accurate, what were we going to get for, what was the false alarm rate going to be like, what was the difference between them. So as well as helping my student, I was sort of teaching myself from first principles. So we use these techniques to recognize attack vectors and to find the origins of the attack as a kind of network forensic mechanism. I would have to say that, just as a sort of an aside, the use of the word forensic is very different for computer scientists, computer engineers and law enforcement. I don't think law enforcement would recognise this as any kind of forensic mechanism at all, because it's sort of so loose in the way that we deal with it. So we have to be highly accurate in what we do for the court. But I can nowadays, and I'm not so scrupulous in what I allow my PhD students to do when they're starting. But I would never ever probably show this to law enforcement and call it a forensic mechanism. So what we've had to do ourselves is to sort of develop an architecture, and this is a very simple block diagram of the proposed network forensics mechanism. So we're collecting traffic, network traffic. We're deciding which features of the traffic we're going to select. We've got 4 algorithms which we're going to use, and then we're going to evaluate the algorithm. So the biggest thing that we had to do during the time I was at UNSW in Canberra, the Defence Academy, was to actually deal with this issue of having no data. Because if you work in a university, you know, nobody in ICT is going to let you collect your own data off of their network. Cisco and all their friends are not going to let you. I have friends in government who won't let me. I have friends in America who said, I'll give you some, but then I know ethics committees won't let me. So the best thing to do was to spend $140,000 on a traffic generator. So essentially what you do is you develop your own known network traffic with known malware in it. So, sorry, go back to this just for a minute. So this was actually, accidentally, one of the best mechanisms for increasing my H-index. Because we developed the first data set, and we made it public. It's on, you know, the Arnet or whatever we have now, the cloud store. And all we said to people, so we put the instructions for doing this in 3 papers. And all they had to do to be able to download our set was to cite our paper, because we told them how to do the research as well. So I call this the third world data set, because I think I've actually supported the research of so many isolated researchers in the Middle East, all over China, India, who have no other way of getting data sets. And we've been really happy to do that. Noor was my first PhD student. But also, I've suddenly become famous as a person who can review papers on data sets. There's a whole new sub-discipline on sort of, it's kind of asking the question, is this a really good data set or not? Now, I don't claim to be an expert on that, but I'll review the papers for them. Because some of them are sort of so obscure that it seems meaningless to me. But there are a lot of us who are putting our data sets out there for other people to get them. And I often, many times, answer questions from other people's PhD students on how to do this kind of work and how to get into here. But I would say for any of us who's coming from a kind of even semi-mathematical background, if you do not know what research to do, or you've got somebody who doesn't know what research to do, this is an easy way into looking at some kind of machine learning AI in a cyber context. Because there are people who are wanting to come back to academia or to change the research direction, and I would suggest that this is a good thing to do. So the machine learning techniques we used were association rule mining, a classification algorithm, artificial neural networks where you, anyway, hopefully you guys learnt all this, didn't you? I'm looking at somebody who's nodding at me. Bayesian models and decision trees. I'm sure every computer scientist learns about decision trees. So I saw these as the easiest algorithms to start with. So what we did, we got our algorithms and we used our own data set, which at UNS ADFA I had a cyber range. So I set up something called the Australian Centre for Cybersecurity, and I left behind the largest master's program in the country. So as a La Trobe professor, I compete with myself. I left behind something really successful. I used to teach undergraduates as well. But so this is the UNSW data set, which we used using a perfect storm tool, which is, generates traffic. And so essentially what we've put in the traffic is sort of, we know all these different kinds of pieces of software or techniques to attack. So we've got fuzzers, backdoors, denial of service, exploits, etc. So we've got naughty, dirty traffic with known malware in there, with 49 features, and we've got training and testing data sets. But let me just watch time. This isn't it. Right, essentially, so we used our data set, we used the algorithms, and essentially we found, I think that I've got the graph here. So essentially, we found that if we used a decision tree, the accuracy was by far the best, and the false alarm rate was by far the lowest. If we used association rule modelling, that's the second best classifier, having an accuracy of 86.45% and the false alarm rate about 13.55. The naive Bayesian one was third in the competition, and the artificial neural network was not terribly accurate, and it had a really high false alarm rate. So this was the first piece of technical work that my PhD student did, using our own data set. But by using net flow techniques, which we don't have to actually go into, we could, if we use this kind of methodology, actually identify the IP address from which an attack was coming. So if we were able, this is highly theoretical, okay, because the bad guys will very quickly switch the IP address from which the attack is coming. So, but if it was totally fixed, we could say the bad guy is there at that IP address. I think that's fine for entry level in your PhD. You know, we can say where the bad guy's coming from, and we can say how good or how accurate this kind of work is. So what I'm actually trying as a first step in what I'm saying to you is you can use machine learning on large amounts of data to come up with a system which you could implement. So today, I've been talking, we're now in the SmartSat CRC, which is, we're looking at satellites. And we're looking at the possibility of doing all the processing on board a satellite instead of having a ground station. And we're looking at how can we secure the data on the satellite. And we're using some form, we're suggesting some form of this kind of technique, much more complex algorithms, much more complex in the way of data and processing. But this illustrates the principle. So the principle is with a little bit of AI. And for somebody like me, I didn't create the data set, and I might be in the situation like I was with one of my PhD students, where his mathematics is much better than mine. Comes out of bioinformatics, because we're crossing disciplines all the time. And so all I can do as a supervisor is look at the results, look at the issues of, you know, accuracy of this system that I've set up. With one of my students, I couldn't decide whether we were creating new knowledge or not, or whether it was good new knowledge or not. I sent to everybody I knew in America, including one of the guys who'd written a book on it, and I still didn't know. So I said, okay, you can do what you're wanting to do, you can submit it to IEEE. And they published it. And then another IEEE publication, some reasonable ones. So I worked out we're probably creating new knowledge, and this was probably okay. But compared to how we normally feel as technical people, you normally know the whole of what we're dealing with. I feel really quite exposed as a researcher, because I keep crossing so many disciplines, that I'm always looking for this perfect person who should help me or work with me or I can mentor, so who knows the algorithms better than me and knows the cybersecurity context as well. Because there are many other contexts that I'm thinking of Nolan's work that we come across in cybersecurity where we have large amounts of data and we need to use these techniques. So going forward, that we're a discipline that's constantly changing. Let me just keep going. That's the end of what I have there, but I think that what I wanted to tell you guys about was, if there are anybody who might want to work in this area, it might be statisticians and mathematicians. It's certainly people who are intuitive with algorithms in ways that engineers are not necessarily. And I think that given that we see exponential growth in data, exponential growth in IoT devices, and we cannot perceive what the future looks like just in terms of national security or being an entrepreneur, this is probably a way to go. So, thank you.